All right, I think we can get started. First, I would like to welcome everyone to today's webinar. My name is Yuan Tian, and I am a content and marketing scientist at Biocytogen Boston Corporation. I'll be moderating today's webinar. And I would like to introduce our speaker today, Dr. Yongfei Yang. So Dr. Yang is the director of the Antibody Research Institute at Biocytogen. He earned his PhD in cell biology from Peking University and then continued his research as a postdoc at the University of Southern California. Before joining Biocytogen, he served as an associate professor and PhD advisor at the School of Life Sciences at Beijing Institute of Technology. So Dr. Yang brings over 18 years of experience in scientific research covering oncology, immunology, cell biology, and genetics, along with 5 years in industry-focused translational research. And now at Biocytogen, he's focused on developing innovative antibody therapies with his work spanning oncology, autoimmune diseases, as well as metabolic, neurological, and cardiovascular conditions. So for today's webinar, Dr. Yang will introduce the exceptional properties of nanobodies. He'll also discuss the application potential of fully human nanobodies in bispecific and multispecific antibodies, XDCs, and cell therapies. So before we dive into today's discussion, I would like to remind everyone that the Q&A box is open. So feel free to drop your questions there during the presentation, and we will address as many questions as we can at the end of today's discussion. So with that, I'll hand it over to Dr. Yang.
Okay, thank you for your introduction. And I'm very happy to introduce our full human nanobodies. And okay, Biocytogen has two product pipeline. First is antibody therapeutics. And we have the fully human mice. One important mice is the RenNano mice. We develop the antibody and make them to the PC stage. And our Zen mice has several different platform. The first one is ZenMab, good for monoclonal antibody, and also ZenLight, good for the bispecific antibody. And also the RenNano mice are good for generate nanobodies. And we also have the TCR platform to generate TCR sequence to generate TCR-T. And also we have TCR mimic platform to generate antibodies, recognize intracellular epitope and to target like the tumor cell. And we also generate a lot of antibodies to target the GPCR gene. And for nanobodies, I think it has a lot of advantages. At the beginning, the nanobody generated from like the camel, and the size is very small, and it can linked with FC, this format. The size is only 15 kilodalton, very small. For traditional IgG format antibody, okay, it's very big. If we want to generate a very small antibody, we need to change to the SCFV format. It has two domains, one is heavy chain and another one is light chain. But the nanobody is only one heavy chain domain, don't need the light chain. So when this is smaller, the antibody is smaller, it has a better tissue penetration. It can go into the tumor environment or other disease environment, has better efficacy. And also the nanobody has a longer CD3 region, so it can generate like a more complicated structure bind to some specific epitope. And for the SFV, because these two domains need to connect with each other, so there is some amino acid is hydrophobic. So maybe it has some problem in the physicochemical properties, maybe easy to generate aggregation. But for nanobody, it's only single domain. So this hydrophobic amino acid will change to hydrophilic amino acid. So it has better physicochemical properties. And because nanobody is very small, so it's suitable for the sub-Q or oral administration. The nano antibody has a lot of advantage. For the uses of nano antibody, we can use in like the CAR-T technique. At the beginning, the CAR-T used scFv format. For one antigen, it's okay because you only have one domain. But now, a lot of CAR-T use two different target gene, can recognize like the two different TA target in the same tumor cell. If we still use scFv, then we need to have four domain. Okay, which first genes which will and also connect to another genes which and will is too complete and very difficult to has the good properties. But when we use the VHH, the nanobody, it has only two domain, and also the two domain is like the has good physicochemical properties, so very easy to generate. The very good for the CAR-T technique, and also the nanobody can link to the FC traditional FC part to generate this structure antibody, like the PD-L1. This antibody are already approved, so filled with FC can extend the half-life of the nano antibody because the nano antibody is very small, so the half-life is very short. If we want to increase the half-life, we can easily just link to the FC domain. And also, it's also very good to generate a bispecific. Like here, this company also use the nano antibody to generate the bispecific. One domain target to the PD-L1 and another one target to the CTLA4. So very simple, only two nanobody domain, much better than like the scFv format. Of course, for the nanoantibody, we can also link to the albumin antibody to generate this kind of structure. There are already several products either approved or has good results in the clinical stage. Like the first one is generated by Sanofi. It has three domain. One, two domain is nanobody targeted to TNF alpha, and another one is targeted to the albumin. So albumin is also can increase the half-life of the nano antibody. This one already approved. And also this nano antibody, the half-life is similar as the traditional IG format antibody. So you inject for 4 weeks. And the second one, this is much simple. Only one domain target to C5 and another target to albumin to increase the half-life. So this size is small, only 25 kilodalton. Also in the oncology area, they generate this kind of very simple structure TCR engager. So it has three domains. One is the CD3. The CD3, I think this is the scFv format because currently there is no good CD3 nano antibody. In our company, we also try a lot, but we still cannot get a very good CD3 nanobody sequence. So here they also use scFv format, and also linked with albumin nanobody to increase the half-life. And another one is the DLL3 nanoantibody to target the tumor cell. This DLL3 is a nanobody. So it's very small, so it has good penetration to the tumor environment. It has good results in the clinical stage. So nanobody has a lot of advantage and can use it in a lot of different area. So in our company, we done this kind of RenNano mice. For our mice, all the all the mice VDG gene replaced by the human gene. And there is no CH1 domain in these mice. We totally knock out the CH1 region, but we still keep the CH2 and CH3 region. So when we use the antigen to immunize our RenNano mice, we get this kind of antibody. So there is no light chain, only heavy chain, and only has V region. There is no CH1 region, but we still keep the CH2 and CH3 region. When we got this kind of structure antibody, we can isolate the antibody and sequence, get the sequence, and then we can use the CHO cell to overexpress either with the FC format or only the VHH, the single domain antibody. We can do both. For our RenNano mice, we have some advantages than previous ones. So previous similar mice, they only replaced limited genes. We replaced all the human VH genes. And for their technique, they just knock out the mice gene and insertion the human gene in another place. But in our technique, we use the in situ replace. So we should generate better quality antibodies. Actually, we test a lot of we test our RenNano antibody. First, we just test the B cell development and the differentiation. As the data showed here, our RenNano antibody, the development of spleen and lymph node is similar to our RenMab and mice, and also very similar to the wild-type mice. And we also isolated the B cell from the spleen and the lymph node. So the number of the B cell is just similar to the wild-type mice and our RenMab mice. So the B cell development is good. And we also use different antigen to generate antibody. Like here, we test the TROP2. This is a TA target, and also CD38, and virus gene, RSV, and two very good candidates for generating antibody, nano-antibody. One is the TFR1, because nanobody, we can use this TFR1 to transport the BBB. And albumin, because albumin is very important for the nano-antibody. It can increase the half-life of the nano-antibody. So we test a lot of different target gene. So as the data shows here, the antibody use different germline gene, and the CDR and the length of the CDR3 region, they are also different. So that means our antibody has good diversity. And also the length of the CDR3 region is a little bit longer than the RenMab mice antibody. We also test the affinity. Like here, we calculate the binding affinity. You see a lot of antibody still has the good affinity, like the nanomolar or sub-nanomolar level. Although the overall quality is a little bit lower than the RenMab, but we still have a lot of good candidate. We can screen them and got the good sequence. We also test some activity because the antibody we always need they have the good activity. Like some antibody we need to have good agonist antibody. Some we need good binding affinity, good blocking activity to be a antagonist antibody. Like here, we generate several good nano-antibody to target the 4-1BB. We test the 4-1BB antibody agonist activity in the luciferase assay. Like here, we use PC. This PC is a good candidate generated from our RenMab mice. And the other three, like blue, green, and orange color, these three is our new nano antibody target for MBB. In this assay, you see our nano antibody has even better activity than our previous RenMab antibody. And our antibody also has good other biologic function. Like for TFR1, we have very good candidate. Because TFR1 can transport the BBB, so this can be very useful for a lot of neural disease target. And we use the PC. This PC is JR141. This is already approved in Japan. We use this intracellular cell line to test the internalization. Like here, we got a lot of antibody to target the TFR1. The PC, this clone has good internalization activity, and also our clones has good internalization activity. Because for the transport BBB, the internalization activity is not higher, better. So maybe the middle level is better. And we also test the physicochemical properties. Like here, our nano antibody has good expression and only one peak, the purity is very good. And also our antibody is more hydrophilic, so very good physicochemical properties. And also here just to summarize our RenNano antibody platform. So our RenNano antibody is from our generated from our full human antibodies platform. We just generated all the antibody sequence is fully human. And currently the immunization is very good. We have good immunization activity. And also our antibody has a good longer CD3, maybe generate better antibody to target specific the epitope. And we have good sequence diversity and has high affinity clones. And we also had some tests. We got the good biological function both in vitro and in vivo. And our antibody has a good developability. For our nano antibody, we can either use in the cell therapy, like to generate CAR-T, maybe also generate the bispecific or multispecific antibodies. We can even generate ADC or REC. So based on our RenNano mice platform, we already started the RenNano 100 project. We already generate antibodies to target about 100 different targets. At the beginning, we mainly focused on the TA target, and now we start to do the immune target, like the cytokine and the cytokine receptor. So both for oncology and for the autoimmune disease, we have a lot of antibody sequence for different targets. Here are several like the sample. Like the first one is TA target. It's a GPCR gene, GPRC5D. And another one is 4-1BB. We will show the agonist activity in our in vivo test. And also the TFR1, we have the BB transporter in vivo results. So the first one is GPRC5D. It's a GPCR, so normally it's a little bit difficult to generate high quality antibodies. But luckily we got a lot of good sequence, nano antibody sequence. And the GPRC5D is a good TA target for the myeloma cell. And also has good results in the clinical stage. Like here, after the immunization, we got like 27 independent sequence. They use different heavy chain germline gene and has different CDR3 region, CDR3 length. We test all the binding ability to the myeloma cells. Like here, all the clones, they can bind to the tumor cell. We also test the binding EC50 activity. So this is the PC. Our clone, PC is this line, and our clone, most of them has good binding ability. So the binding EC50 activity is better than the PC. So we have a lot of clones. And we also test the internalization activity because for like if you use the nanobody to do the CAR-T or generate generate TCR engager antibody with CD3, maybe you want an antibody with low internalization activity. Then you want to generate a ADC product, maybe you want a antibody with high internalization activity. So we test all the antibodies. So some clones show better internalization activity than PC. Some are similar. So we just list the final results here. So like the results show here, some clones like here, the internalization activity is much better than PC, and some clones, the activity is similar to PC. So high internalization activity good for ADC product, and a lower activity one may be good for CAR-T and for TCR engager product. Another one is 4-1BB. 4-1BB, we want agonist antibody because 4-1BB is important for the T cell activity, can activate the T cell to kill the tumor cell. We immune the RenNano mice with 4-1BB antigen, and we got more about 275 clones. All these clones can bind to both human and monkey genes. After the affinity test and the function assay, we finally got 7 good candidates. They can bind to both human and monkey 4-1BB target, and also has a good agonist activity. And this activity is also cross-link dependent. This is important because if it's cross-link independent, the toxicity may be too high. So if it's cross-link dependent, we can generate a bispecific to have good efficacy, but with limited toxicity. Here is the results. We use this HBM 708, this clone as a positive control, and also use another two. And for our 7 RenNano antibody, we also test the affinity. So all the affinity bind to human and monkey, the affinity is very good and similar to the positive control. Like here, all 7 clones have good affinity. And we also test the agonist activity in the cell line. So we use this reporter assay system. Like here shown, all the 7 clones have good activity. This urilumab is in cross-link independent clone, so the activity too high and has toxicity. Our clones, they are cross-link dependent because in this figure, when we add the FC receptor, they have the activity. But in these results, we only add the jerked cell without the FC receptor or clones. There is no agonist activity. So our antibody is cross-link dependent agonist activity. So also the similar results for our another 4 clones, 4, 5, 6, and 7. So they all have good activity in the when cross-linked with FC receptor and with no activity or very limited activity without the Fc receptor. We also test the in vivo efficacy. Like here, we generate this kind of bispecific antibody. Like here, we use B7H4 and link the 4-1BB nano antibody in the C terminal. And when the B7H4 bind to tumor cell, it can cross-link and then activate the 4-1BB. In our this in vivo assay, we show like here, like the two clone, RenNano1 and RenNano2 has similar efficacy as the positive control. So also has a good activity in the in vivo experiments. So the last one is the TFR1. It's another name is CD71. Similarly, we also immunize with the RenNano mice with C7 protein, and after screening, we got 20 good candidate, has good affinity to both human and monkey TFR1. And we use this candidate to do the internet activity, and then also we detect the in vivo BB transporter assay. Like here, these are the results for our nanobody affinity. So bind to human and also bind to monkey. Three of them, antibody 9, 26, and 38, these three has good good affinity to both human and monkey. We also test the in vivo. Like here, we just injection the antibody into the mice, and then we isolate the brain tissue, and finally we isolate the parenchyma to test how many antibodies cross the BBB. In this assay, we also use the Japan TFR1 antibody as a positive control. This antibody, they use the traditional IgG format. Our antibody uses a similar format. The R is the nano antibody, not the FAB. But also similar, we filled with the same FG. We use same one, human IgG1 with an mutation, similar to the positive control. As data showed here, our antibody, you see the positive control is a blue line, like here, blue line. So the positive control can cross the BBB, and our antibody has even better activity. Like here, the best one is 38, this one, and also another good candidate is 26. The ability to cross the BBB is much better than the positive control. And these two clones already used by several partners. They already use our antibody to repeat our experiment, and they got similar results. So our antibody is very good to transport the BBB. Okay, that's all. So very happy to answer your question.
Thank you so much, Dr. Yang, for the informative presentation. Looks like we do have a couple of questions that have come in. So let's take a look at the Q&A box. So the first question here, what are the modifications in RenNano FAB region?
Like here, I showed here, in the FAB region, we just for all the nano antibody, we don't need the light chain, and even for the heavy chain, there is no CH1 region, only the V domain, so much simple and only a single domain. Okay, that's all.
Okay, thanks, Dr. Yang. Another question that came in, do you offer RenMice or provide the RenNano service? I think this is more like a BD question. Maybe Natalie can handle this.
Yes, we do have licensing options for these mice.
Yeah, we have licensing, co-development. We have several different partnership models. If you're interested, feel free to contact us at info@biocytogen.com, or you can contact our BD team at bd-licensing@biocytogen.com. We will give you more information there. All right, next question. In RenNano mice, why CDR3 is longer? I think based on the design, only CH1 is removed.
Yeah, good question. Actually, even not only or RenNano mice, I think even for the nano antibody like generated from camel, the CDR3 region is longer. I think it's some reason in the evolution happened. I don't know the exact reason, but it really happens. In our RenNano mice, although the immunization time is only like about 3 months. Actually, we need 3 months to do the immunization. But I think without the light chain, only have the heavy chain, the antibody you will try to generate the good quality antibody. Only the CD, some antibody has longer CD3, maybe has good like the affinity or the biological activity. So because without the help of the light chain, the heavy chain itself need to like have more powerful ability. I think something happens in the maturation of the antibody sequence. Yeah, I don't know the exact reason, but it really happens.
Okay, thanks, Dr. Yang. Next question. How much percentage of the systemic TFR1 HCAB dose or heavy chain only antibody dose crosses blood-brain barrier?
I think the totally, I think it's about 1 to 2% can cross the BBB or nano antibody. Like the results shown here, I think overall the body control is about 1%, and our good antibody is better than 2%.
The next question, how does TFR1 heavy chain only antibody affinity correlate with BBB crossing?
Yeah, this is a good question. Actually, for the TFR1 transporter BBB, at the beginning, Roche has published several papers already approved. The affinity in this project is not like the high affinity is better. Actually, the middle, even a little bit lower affinity is better. In our experiment, we also approved these results. Yeah, we got the same results. Uh, uh, too high affinity is not good. And we also found the same results as the Roche. Even for our antibody, there's this antibody is 26. The monovalent structure is better than the bivalent structure because monovalent has even lower affinity. And I think the affinity is like there is some like the window, I think. Too high is not good, too low is also not good. There is some like the middle region is perfect. Currently, although our 26, this 26 is already very good, but currently we still modify the sequence. We change the sequence to generate some new sequence, a little bit higher affinity, and also try to generate some sequence with a little bit lower affinity. We are testing. Maybe we can find another sequence like even maybe a little bit lower than the 26 it has even better ability. We still need to try, but I think overall the middle level affinity is also good. And also for the internalization is also similar. Not means the high internalization activity antibody is good, because it need to transport internalization to the endothelial cell, and also need to trans the membrane into the BBB. So high internalization activity, very high, is also not good. It's also the middle level is good. So for TFR1 transport BBB, yeah, this is very different from other project.
Next question. Are there any nanobodies reaching p-molar KD as antibodies?
Actually, it's very difficult to generate p-molar level antibody for the nano antibody. But it also depends on the target. Overall, it's very difficult. But for some target, it's really happen. We can got the p-molar level affinity antibody. But overall, it's difficult. So it depends on the target.
Okay, thanks. Next question. What role does the tumor microenvironment, or TME, play in modulating the expression of GPRC5D? And how does this impact the binding efficacy and therapeutic window of anti-GPCR5D nanobodies?
Yeah, for GPCRC 5D, it's a good T target. So when the environment changed, like maybe the patient treated with some drug, the GPRC 5D, the expression level will be increased. It will increased. So in this case, of course, when the expression level is higher, of course, the antibody can bind more to the tumor cell, recognize better to the tumor cell, and increase the efficacy, therapeutic efficacy. I think overall it can increase the therapeutic window.
Next question. What is half-life of nanobodies generated from RenNano mouse?
If you only use the VHH domain only, because it's too small, it's only 15 kilodalton, so it will be cleaned very quickly. I think we test in mice, it's very quick, even less than one day in mice. But in most cases, we don't need this kind of structure because it's too small. Overall, we will fuse with either FC or fused with albumin antibody to increase half-life. Okay, actually, when we have that, yeah, here. Yeah. Okay. Well, when we fused with FC, I think the half-life is similar than the traditional IgG format antibody. But fused with the albumin antibody, it really depends on the quality of the albumin antibody. Like here, even these three products, they already tested in the clinical stage. Like you see, the Sanofi one, albumin, the half-life is much better. It's 4 weeks. And also the AZ one, it's about 8 weeks. But for this TCR engager one, the half-life is about 3 to 5 days. We test this results in our mice. We have the fully humanized albumin mice. We tested in our albumin humanized mice for the PK. And in the mice, Sanofi one is good. The half-life is also very similar to the like the IgG FC format, like the traditional IgG format antibody. And we also got a lot of albumin antibody sequence. So some sequence it can has a good binding ability. The affinity is good, and also maybe the epitope is very close to the Sanofi one. Then the PK is good in mice. But some clones affinity is lower, and maybe the epitope is not good. The affinity and the PK is it's not good. So that means if you only use the VHH domain only, definitely it's very short. Maybe good for the like the RDC or something, but not good for the like the oncology or for autoimmune disease. So very limited product is only use VHH. Most cases we will fill with FC. With FC is normal, and another choice is fused with albumin antibody. It really depends on the quality of the albumin antibody.
Next question, what is timeline from production to select of final?
Okay, yeah, good question. For the nanobody immunization, it's much difficult than our RenMab mice. For RenMab mice, in most cases, we inject for 4 times, inject antigen for 4 times. But for generate high quality RenNano antibody, even the immunization, we need about 7 to 9 immunization. That means we need even 3 or even more time to 3 months, even more time to do the immunization. We can get a good titer, and we can start to get the sequence. So from the if you give me a new target, it's like the TA or some like the cytokine. I think for immunization it's about 3 months, and then we use our beacon system to get the sequence. It's very good. Only several days we can get the sequence, and we start to overexpress the new antibody in like in the CHO cell, and then to do some like the basic screening, like the binding to human and monkey antigen, and then test like the affinity, or you want me to test like some like the internalization activity. I think overall, I think we can finish about in about 6 months. But if you want me to screen more function, it's really target dependent. Depends on how complicated all the functionality is different.
Are the humanized mice contain human framework and human CDR? Could you explain more about humanized mice generation?
Oh, yes. Here, okay, here. Yes, for the humanized mice, like here, we just change all the VDG gene. We just replaced all the mice gene with the human gene. So the antibody, the V region, both the CDR region and the FR region, is human gene. So the sequence is the human sequence. But for ZMAB, like the ZMAB, ZMAB still has CH1, but the CH1 region, CH2, and CH3 is mice sequence. But it's okay because when we got the antibody, we can do the sequencing to get the sequence of the CDR region and FR region. We can do cloning to the express vectors. So CH1, CH2, CH3, it's mice gene, it's okay. So yeah, because we totally changed the sequence, so the CDR region and the alpha region definitely is a human sequence. But it still has like the mutation in the alpha region. Even we got the fully human antibody, the alpha region has some like the mutation. That's similar as the wild type mice. For RenNano, it's the same as our RenMap. So all the VDG gene changed to human. So the CDR and the alpha region sequence is human. But in this mice, we don't have any light chain gene. We totally delete all the light chain gene. And we also do a lot of modification. We change the sequence and we delete the CH1 region.
Next question. In BLI assay, what is the general KD value range of a good nanobody?
Yeah, it's also totally different. It really depends on the target. I think for the BLI, I think in most cases it's about the nanomole level, like -8, -9, or even -10. It's good quality. It's just the same as like the traditional IgG format. Because even in our assay, like the affinity assay, like here, the affinity assay, we don't use like the VHH domain only, the nanobody only to test. We still fuse with FC format because we fuse with FC tag, we can easily to purify the protein. Of course, if you want the VHH domain only, we also can fuse with his tag, use his tag to do the purification. We test the several target. You use his tag to do the affinity test. The results is similar as the FC tagged results. So the results is similar. So I think that's the same as the IgG format. The affinity is the same requirement for both the normal antibody and the nano antibody.
Another question, what technical challenges did you face in developing RenNano anti-4-1BB heavy chain only antibodies, particularly regarding antibody stability and efficacy?
Yeah, so for 4-1BB, we already introduced. We finished the in vitro experiment and finished some like a basic in vivo experiment to show the good anti-tumor efficacy. But we still need to test the drugability and also like maybe the other some like the immunogenicity properties. So I think in most cases for the nano antibody, it's all the same as like the nanobody generated from camel. Most of the sequences they has complicated modification, especially for the glycosylation modification. So some clones maybe have good activity, but the drugability has good has some challenge. In this case, we want to generate more sequence. We really have some case. We have a lot of candidate. Some sequence has a drugability problem, but the other sequence there is no problem. We just choose no problem as to continue our experiment. But in some cases, we don't have that many choice. Then we need to do the sequence modification. Just like the IgG format antibody. We need to modify the like the glycosylation amino acid change to another amino acid and repeat the function assay and also repeat the drugability assays. So for not only for 4-1BB, I think for all the target gene, all sequence, overall the antibody, we need to very careful about the drugability assay. It's not easy to get a very perfect nanobody antibody because I think most people realize that the nanobody is very good, but currently we still have limited product in clinical stage. That not means people don't want to try this kind of project. I think a lot of people tried, but if you want to get a perfect nano antibody sequence, either from like the camel or from other mice or other technique, this is much difficult than generate a normal antibody. So overall, nano antibody is challenge from immunization basic screening and the drugability, they all challenge.
Another question that came in, do VHH domains on their own have enhanced the penetration through the BBB compared to the heavy chain only antibodies?
We didn't test this experiment currently. Because I think because if we only use VHH like the nanobody only the single domain, it's too small. I think the PK the half-life is too short. So currently we still fuse with FC, but later maybe we can try to fuse with albumin. We never try the VHH only in this test in vivo use the mouse model. We never did this experiment. I don't know currently.
The next question, how do you deal with the FC activity?
FC activity. I think for nanoantibody, it's just change the FAB part to a very small domain, very small antibody. If you still feel the FC, I think it really depends on the target. Okay, like okay, maybe like here, yes. Like here, if you want to generate like the antibody like PD-1 or PD-L1, okay, because you only use blocking activity, you don't need any ADCC or ADCP effect. So the FC is FC silence, like use LALA mutation or NA mutation. So there is no ADCC effect. If you want to like generate antibody, like you want to have the ADC effect, then I think you need to choose the wild type IgG1. So there, the FC it really depends on your target and depends on the MOA, the mechanism. It's not fixed.
Next question, how's the developability of your nanobodies? Are there issues or concerns about aggregation, which often occurs with SCF with or VHHs?
Yes, I think even our antibody, the aggregation still need to it's still a problem we need to solve. But the likely is if you got the like the antibody from camel, you can only get limited number because its cost is also much higher than our mice. With our mice, we can inject more mice, got more sequence. With more candidate sequence, we can in the screening we can choose the sequence without the aggregation. But overall, as I explained, overall the aggregation still a problem. Like the like even you use the like the wild type mice, you still have some sequence has aggregation problem. So the percentage of the aggregation, I think is similar. So even in theory, the non-antibody, they change some amino acid, they are more hydrophilic. The aggregation should be reduced, but not all the sequences change the hydrophilic amino acid. And there is you still need to do the experiment to screen the good sequence without aggregation problem. Not all sequences has good properties. We still need to do more screening. But we can got more sequence candidate sequence. We have better chance to get easily to get a good candidate sequence without the aggregation. Like the TFR1, we actually now we screen more. We got more sequence. Currently, we got more sequence, and we have very good sequence. They they have very good physicochemical properties. No aggregation, the TM is high, and it's very stable. Expression level is very good. So we even didn't do any modification. We just got a sequence, very good biological activity, good druggability, and no aggregation. So that means use the mice to do the antibody discovery. You have more like the library. At the beginning, you got a mouse sequence. You have a very good library to do screening. So much easier to get a good candidate.
Thanks, Dr. Yang. Unfortunately, I don't think we have time for any more questions, but feel free to contact us for further questions through email. You can email info@biocytogen.com or to our BD team, bd-licensing@biocytogen.com. We will be happy to handle further questions. Okay, I think that's all we have for today. Thanks, everyone, for answering these questions, and thank our audience for participating. Just so you know, this webinar will be available to watch on demand if you did miss anything today. And please don't hesitate to visit our website to learn more about our projects and services. In addition to RenNano, you can also search for other target programs or platforms we have on biocytogen.com to see a broader list of targets and our current progress of discovery. And we also have more information to share in the Biocytogen YouTube channel, where you can find more details about us and also our previous webinar recordings. Again, if you have additional questions about RenMice or RenBiologics, feel free to reach out to us via email. So thank you all for joining us today. And that's all we have for today. Have a wonderful rest of the day, and we hope to see you again soon. Thank you.
Thank you.